Okay, so we'll continue on impulsive maneuvers. We have a few more to cover. Before I forget, so Monday, no class. I'm out of town. And then Wednesday, he's teaching a class about... Huh?
Is there a video lecture?
No class, nothing, zero. If you want, I can give you something more to do, but you can exercise with Astrogator, for example. Patrick will show you how he got some software from the NASA's website, is that correct? And customized it in MATLAB to run simulations, high-fidelity simulations around Mars. The SPICE tools, that's SPICE Toolkit, that's what it is. So he will take that lecture, and we're doing pretty well. Compared to last year, we're a little bit ahead, so it's fine, we're in good shape. Now Friday, I will teach, unless the sponsor from NASA Kennedy who's coming for a kickoff meeting here wants to give a lecture. I have a couple folks from the Launch Services program coming here. They manage rockets and launches and real satellites, so they may decide to give a talk. The only thing is that they can't really share and project slides because of export control, I don't know. So I'm not sure if it's really worth it for them to come here and have nothing to show. So we'll see. Otherwise, Friday is regular lecture. Well, Wednesday is regular lecture too. So what he covers will be part of the class. Can we share the code with them once you show it? Is that something easy to use?
Yeah.
We'll see.
It's kind of a pain to set up, but I can give you the code.
Well, Mars is, current interest, so we wanted to give you that option too. Okay, so let's steal from a circle to another circle, but let's see how we can save some fuel adding one additional impulse. So we're going to see Bielliptic Hohmann transfers. And you have to bear with me, I have to draw the old version of the Hohmann transfer, the one we've seen with two impulses, and the new one on the same plot, the same drawing, not plot. So we have and we also are going to do everything like we did so far, going from the small circle to the outer circle, but you can reverse the situation, of course. One is the trajectory I start from. We call F, if you want, the focus of all the conics, which is the Earth. Call this point A. I'm going to start from here and say that you want to go to a bigger circle, which is, I want to make it too big, otherwise, which is this one, which is supposed to be a circle, okay? And we call this trajectory 4. Will be clear for a reason pretty soon. Okay, this is the Hohmann transfer, so let's call this H. 1, H4, and then, so this is what we've done so far, okay? Give a few names here, C, D. Okay, I'm not going to add anything for now. The radius of this is RA, of the inner circle. The radius of the outer circle will be clear why I'm not calling it B in a few minutes. I'll call it RC. I'm trying to be consistent with what you will find on the book, chapter 6, when they talk about Hohmann transfer and Bielliptic transfer. So this is what we've done before. We go and increase the velocity in point A, go on a bigger semi-major axis, such that this transfer ellipse has the apoapsis at a point which is at this distance RC that I want to obtain. So here increase the velocity again so that you circularize your orbit. By the way, all these maneuvers we've seen, they are changing semi-major axis and eccentricity. I haven't spelled that out, but that's what I'm doing with these impulses. I am changing semi-major axis right here, and then here I'm changing the semi-major axis and eccentricity. So in both cases, you're changing semi-major axis and eccentricity at the same time doing this, right? Increase semi-major axis, increase eccentricity, increase semi-major axis, decrease eccentricity. That's what we do. Okay. So this is expensive, as every maneuver, may be more or less expensive. So an alternative to reduce, in some cases, it depends, we'll see when this is true, the consumption is and this is a rule of thumb, is taking a little bit more time. Getting to the circle, taking more time and doing this. You still go to an ellipse, but its apogee is outside of the circle I want to reach. So you go from A to point B. That's why I didn't use B before. And so here I'm going to call this distance now RB. Okay. From planet to this new apoapsis. That still requires an increase of velocity, of course. Okay. You still go into a bigger semi-major axis. And then you do another burn here, such that this other ellipse that you're creating is going to be tangent right here in C. Burn here, and another burn here. So it's a 3-impulse maneuver. And what do I call this? I call this top ellipse 2, and I call this bottom ellipse 3. So that's why we have 1 Hohmann, 4 is my final goal, and these intermediate 2 ellipses that I'm creating are 2 and 3. So now you're adding an impulse in between initial and final, but as you can imagine, you're adding quite a bit of time. This ellipse has a bigger semi-major axis, which means has a longer half period, and even more for this last one. So you're paying a price for saving fuel, if you're saving fuel. We don't know that yet. But that's the idea, is that you are going to hopefully have a maneuver here that is tiny, and this one as well that is tiny, so that it's convenient to do this rather than fire here and fire here. I'm going to ask you a question here. The burn I perform in A, if I want to go to the H trajectory, or trajectory number 2, which of the 2 is going to be more expensive? What do you think? 2. So there must be a combination. I mean, people thought about this, so I'm telling you, yes, there are some combinations when this is convenient, but the first burn is going to increase the cost, for sure. So it's whatever happens after that, so this burn here and this burn here, they have to be less than what you would do in point D with the Hohmann transfer to make it worth it. Plus, you need to have enough time that you can wait. It depends on if you're in a rush or not, because you're adding substantial amount of time here. Make sense? So I will go through some calculations here, and then show you a graph that is on your book. I think it's figure 6. I didn't want to project on the screen just for this image, so I just reproduced it here by hands. 6.8, that basically compares in a parametric way the Hohmann transfer and the Bielliptic transfer. But before I do so, I'm going to manipulate a delta V 6.8, yes. The way we write the delta V for the Hohmann transfer first, we're going to normalize it the way the book does. And then as uncollected homework, the same thing I've done in the past, you do it for the Bielliptic, which is just an exercise, symbolic exercise, to normalize it and obtain the formula that they give you on the book. So let's start with the Hohmann one. What I'm going to do is 2 things, is normalize, because this is how it's presented in textbooks, the delta V's by dividing them by, I don't want to repeat by, the velocity on the first orbit, which is a circular velocity, call it V0 for example, that's the start, which is mu over RA. I think I called it RA, yes, this one. So every delta V that we'll find will be normalized. We would divide it by that quantity. And 2, normalize the R, what do we have? RB and RC dividing by RA. So everything is basically referred to that initial circle. The delta V is divided by its velocity, circular velocity, and the RB and RC are divided by RA. So that's how it's presented on textbooks. That's how you can analyze that graph that I'm going to show you, where we have different areas. In one area, the bielliptic is more convenient. In another area, it's less convenient. And it will all be based on where you can position this distance. There are some distances of RB that make the bielliptic more convenient than the Hohmann, and other distances where that doesn't happen. And it's up to you to choose if you can wait that extra amount of time. Okay, so I'll do it for Hohmann. You guys do it for the bielliptic, because it's really just doing it one more time, because it's one more burn. So, usual exercise. What do we do at point A for Hohmann? We compute the velocity, point A on trajectory 1, and that is actually what I call V0, right? I'm going to divide everything by this quantity here. Velocity in point A on the H trajectory, the transfer is square root of 2 mu square root of 1 over the position where you burn minus 1 over the major axis of the orbit where you're going to, which is RA plus this distance F to D, which is RC, right? So I'm going to continue here so that we can get the form you find in your textbook, which is, well, you just do common denominator here, RA plus RC. Here we have RA plus RC minus RA. And so your velocity AH is square root of 2 mu square root of RC over RA plus RC. Now what I said is that I want to basically make this RC disappear in this case and normalize by V0. So what do you do? You rewrite this the following way: square root of mu over RA that multiplies, now the square root, 2 RC, RA plus RC. Nothing special, right? Now this is my V0. So I'm going to continue here and say that this is V0. Now, I want to normalize distances divided by RA. So I'm going to take this fraction here and divide top and bottom, numerator and denominator, by RA. That gives me, and I'm going to give that fraction a name, of course. That gives me 2 alpha 1 plus alpha, where alpha is this RC over RA. That's the velocity in A to be on the transfer ellipse. So that means, yeah, that's it. I'm not going to do anything else. I'm just going to leave it there. The delta V will be the difference of this velocity and this velocity, of course. The second impulse, I'm going to start from, doesn't really matter, but let's do the velocity in D on the transfer ellipse. That's square root of 2 mu, square root of 1 over. Now I am at that point that I call D, just because I couldn't call it another C, but the distance is RC, right? So this is RC, and this is the same major axis I had there, RA plus RC. A few more steps. Square root 2 mu. What do we have here? RC, RA plus RC. I have RA plus RC. Now it's minus RC. Take out the RA. What is this going to give you? Is 2. What do you think? RA if I take a 1 over RA out of that, what do I get? Keep in mind that that's parameter alpha that I have defined. For example, this, right? Yeah. So this is another V0 because I'm pulling it out, and I still have these R's that I don't like. So I divide top and bottom by RA again, and I should get something like this. Okay? I'm just putting these in the form that you find in textbooks because it's all parametric. As you've seen also for, what did we do the other time? The delta V3 prime and delta V3 that we were comparing, they were all, those plots, those 3 plots we looked at, they were all normalized. They are 8-dimensional values. So I don't know if I don't need to retain this, right? Gone through the calculation. I'm going to just copy what I have up there. This is V0 square root 2 alpha 1 plus alpha. Remember, alpha is I'm going to write it up here. Okay. V0 is square root of mu over RA, and alpha is RC over RA. Okay, I have VDH. Just going to put it here. It's down there. V0 square root of 2 alpha times 1 plus alpha. So what is left? I have to finally compute the velocity in D on trajectory that I called 4. And what is that? I'm just doing the Hohmann. I'm not even doing the Bielliptic one. Yep, square root of mu over RC. So if you want to take out an alpha here, you divide, you extract 1 over RA, you get V0 square root of 1 over alpha, or 1 over square root of alpha, it's same. So now I have the 4 velocities, let me put it down here, that give me what I need. They're just in symbolic way, they're just a function of that V0 and that alpha, but I know exactly what those are, so your first burn will be this minus this. Second burn will be this minus this. Okay, the delta V total on the Hohmann transfer, if you take them all together, again, D4 minus DH plus AH minus A1 is going to look like this. 1 over square root of alpha minus square root of 2, 1 over the square root of alpha that multiplies 1 plus alpha, plus square root of 2, square root of alpha over 1 plus alpha, minus 1. And if you manipulate this common denominator between these two, nothing special, you get what you find in your book, which is this expression. I think this is the way it's presented to you on the textbook. Okay, so now, if you want dV total normalized, just divide both sides by V0, and that's basically the piece that you see in your book. Why did I go through the pain of doing this? So that you can do it for the Bielliptic. It is exactly the same story. You compute 2 velocities at each point, keeping in mind where you are in that point, because that goes into your velocity expression, right? Our velocity is always equal to square root of 2 mu, square root of 1 over where you are, minus 1 over 2A, the same major axis on the orbit that you're interested in. You just repeat that over and over again. So I've just done it for this case. As an uncollected homework, you do it for this other case. 3 burns, here, here, and there, with an addition. So I'll post it as well, but, and do this. You should find a similar expression for delta V total bielliptic over V0, which is some expression, some function of alpha, the same alpha that I have there, which is RC over RA, plus something else. There is an additional radius here that your book calls beta, which is RB over RA. But the procedure is exactly the same. And I'm not even sure that I have the final expression here. It's on your textbook. What we care about is how these two compare. Let me see if I can give it to you. Why not? Yeah. Okay, so yeah, here it is. So this is the one of interest for Hohmann. Okay, this one here. And for bielliptic, we have it's a little bit longer, quite a bit longer. Okay, minus 1 plus square root of A over square root of A plus square root of 2 over beta 1 plus beta, that multiplies beta minus 1, plus, finally, that's not too bad, square root of 2 alpha plus beta alpha beta. That's what it is. So this would be your parametric expression, normalize delta V with the bielliptic. Try to find this expression. The procedure is exactly the same. Extract from each velocity, just bring out the square root of mu over RA, that V0, take it out, and everywhere you see a radius, divide by RA until they disappear, and code beta RB over RA. I have the solution already posted. It's 2 or 3 pages of calculations. Tedious calculations. What I care about is how these two compare, as I said, which is the following plot that you can obtain running several cases. For example, in MATLAB, basically plotting this, comparing these delta V's for different values of alphas and betas. Which side can I erase? I don't want to erase the transfer, really. Maybe here. So, if you analyze the delta V's having on the x-axis RC over RA, which I think I called alpha, and here you have RB over RA, and this is the line of RB equal to RC. Your book doesn't really have it the same scale. It's a little inclined because this is where you are going to play with RB. You may want to increase RB quite a bit to make it convenient. So this is RB equals RC. There's nothing here, really, because if RB collapses to RC, you're doing a Hohmann transfer. Okay, so that's the limit that cuts out a piece of the plane. And then there is a value of 1194. So you basically have to plot these to convince yourself that this is true. It's not something you can do it really by hand. It's an asymptote, and there is this line here that is separating basically the plane in 2 areas. And I apologize, I did not save this value here on my plot. It's on the book. I think it's about 15, but I didn't write it down. It's slightly after 11.95. So 94. So this is bielliptic, meaning that if you come in with a certain RC that you want to obtain, normalized with RA, basically a ratio between inner and outer circle, and you choose RBs that are in this area, then it's convenient to do that. It's convenient to do 3 burns. It's going to take a lot more time, as you can see from this picture. While here on this side of this line, it's all Hohmann, classical, 2 burns. That's it. Basically, along the same lines of that plot that those 3 plots that we discussed last time, going from an ellipse to another ellipse, there are parametric tables. I mean, this plot you can see it as a table. There's basically graphs that you can refer to see if it's more convenient to do one way or the other. That's all. Yes.
So everything under that triangle, you really don't want to do?
No, RB, everything. That's a good point. Everything below that is something you could analyze that is probably very inconvenient compared to Hohmann as well, is you doing this, is going inside and then going here. Which I suspect is going to be a lot more expensive. People don't do it.
That like dotted line, that doesn't define anything else in the
No, this is just it's an asymptote for this. So it's just so that I can divide. So if you forget about this for a moment, this area here is just divided by this curve here. It comes out of plotting those, testing for different points, all those delta V's, as a function of alpha and beta. So yeah, that's a good point. It's basically going inside, which no one does, because it's going to be probably very expensive compared even to Hohmann. That's a good exercise to test on Astrogate. Why don't you do that? Just do the Hohmann transfer that we finished last time, and try to do a bielliptic where instead of going out, you go in. Make sense? Any other questions? There's nothing really that exciting about impulsive maneuvers. They are relatively easy to deal with, other than these graphs and ugly solutions. They're just changing velocities in specific locations. A more interesting maneuver, at least to me is more interesting, more fun, is a refacing maneuver. So forget about changing your orbit. We can move on. Yeah, we have time. So again, I'm leaving you with computing this expression yourself. I have my notes already online, if you want, but do it as an exercise. It's a good exercise to compute delta V's symbolically. You can also, in SDK, if you want, verify that this is true. Pick a few points in this plane. Why not? Pick one here. You will have to set Astrogrador to solve for 3 burns where you're going to a smaller, to a point here, B, that is less than RC, and then go there and see how much delta V you get. But yeah, yes?
Is that plot still valid for desired orbit? Is it circular or like an initial orbit?
No, this one is done for circle to circle. Okay. I don't think your book even has the ellipse to ellipse case. I think that will make things even more parametric than this, and probably you have to do on a case-by-case type of analysis. In other words, probably it's not enough to analyze the delta V as a function of only alpha and beta. Is this alpha? Yeah, this is alpha. Alpha and beta. So if you're going to add more complexity to the shape, it's going to be not that straightforward to do in a plane like that. Yeah, I don't think your book covers that case. But yeah, his question is what if this is an ellipse and this is an ellipse? Yeah, you can still do either 2 burns, like we discussed last time, or this. It's just not that trivial to analyze with equations. You will have to do on a case-by-case basis. Because all these are no linear expressions if you look at them. That is the problem, really. Any other questions? Okay. So again, you have enough to play with, especially after the astrogator examples that we have seen. You can really test all these nice maneuvers, play with more than one impulse. Let's say now that we want to do something different. Phasing. Do I call them refacing? Well, refacing, phasing is the same story. Example of what this means: your planet, your geostationary orbit that goes around the planet on the equatorial plane. You want to cover a certain location on the planet, which means your slot on the geostationary belt has to be more or less above the longitude, but you're not there yet. You've been injected into orbit for some reason. You're here. You need to correct this angle. You still want to be on that orbit. You are already on the right orbit. You're just not in the right position. Make sense? This is relative to the Earth that is rotating, right? So this is rotation axis. So from the Earth's perspective, if you are in geostationary orbit, you're not really moving, even though we know that these satellites are running around on their orbits. But this is what refacing or phasing really means, is that for the most part, you are already on the right orbit, but you don't like where you are. This is an example. Another example is circular orbit. The space shuttle is here. For some reason, ISS is here. They are more or less at the same altitude. They're just chasing each other, and you need to get to the ISS. So you have to correct for this error that you have in phase. That's why it's called phasing maneuver. The idea is, well, you can do everything here. You can do in many different ways, especially with continuous thrust, but we're not doing that yet. We're still doing impulsive maneuvers. The idea is still a two-burn maneuver, where you start and end the maneuver at the same location. Let me explain it with another sketch with elliptical orbits. This is your focus. If I am on this orbit, say here, and I burn and I go to a slightly bigger orbit, and then I burn exactly the opposite burn at the same location, I just go back to my initial one, right? Except the time that has gone by is a little longer than my, what do I call this? Call this 1. Than my original orbital period. If I go on 2, I know that T2 is slightly, depends on how much I'm burning here, is slightly greater than T1 because A2 is greater than A1, right? There is proportionality between period and semi-major axis. In particular, this is what it is. A is T square root of mu over 2 pi at the 3 over 2. I'm sorry, 2 over 3. It's the opposite. If we do it this way, yes. So anyways, bigger orbit requires more time. Makes sense. Or if I do this, I retroburn there, and then I correct and accelerate when I get to the same point. I end up on still orbit 1, the continuous line 1. I've just gone a little faster here because it's a smaller orbit, right? And so if you go back to this example, say that the direction of flight is this, and I want to rendezvous with International Space Station. I want to catch up with this, right? But I am just chasing it because it's exactly the same orbit. What can you do? You can do a lot of different things. But with that in mind, basically go into either a slightly faster or slightly slower orbit. Well, you can go inside, burn here, go to an elliptical path that is a little faster than the circle, And you have to size it the right way so that by the time you've done this, the ISS has done all this, and you guys meet right here. Make sense? That is one way to do phasing. Or you go outside. Now you're moving slower. So you still have to time it in such a way that the ISS has gone around and has done it more than once so that you meet there. Make sense? Yes?
Is it cheaper to decrease your orbit or increase your orbit in touch?
It is a matter of time. The way it works is usually if you allow to wait for longer, it's always cheaper. It's just a matter of time, as we'll see. I'll do an example. The example is going in, but it really works the same way going out for the simple reason is that what matters is how much you change your same major axis. That's going to drive the amount of delta V you need, because you need delta V to decrease the same major axis or to increase it. It's just the sign of the velocity that you're going to change. And so the bottom line is it's time. So, for example, just to give a better idea on this response, I can do a very tiny burn here where my inner orbit is ridiculously close to the original one. And I'm moving faster than the original one, faster than the ISS, but the difference in velocity is so tiny that you need to go around multiple times here to allow the ISS to go from where it is and almost do an orbital period, or orbital period minus this angle, and be here again. So I can actually do phasing maneuvers, and the same if you go out. You can slightly increase your same major axis, but almost be in the same orbit, so that you have to wait so many revolutions to actually be in sync again that it may take forever, but that drives down your delta V. So basically the delta orbital period or delta same major axis that you're creating is driving how much change in velocity you need, right? Because again, remember, this is the velocity expression. I'm going to write it again. Square root of 2 mu, square root of 1 over r minus 1 over 2a. When you do impulsive burns, you keep this constant. You're going to change these with all the maneuvers that we've seen basically so far. So if this is the velocity before and then you do it for a new same major axis and that's your velocity after, the difference is going to be driven by that. The same major axis that you impose. Yes?
You also change your eccentricity?
Yeah, you change your eccentricity doing that, slightly.
Couldn't you just change your eccentricity instead of changing your velocity in a way? And then eventually you'll go with contact in the middle?
You change your eccentricity without changing your velocity. How do you do that?
Energy of your orbit. You're always changing your eccentricity.
Right.
Instead of going to small orbit, you can just change your eccentricity so that the positions will change over time. Then when you actually time it so that.
So you want to obtain an orbit that has the same major axis, which is the same as this.
That'd be less energy.
I'm not sure I'm following the question.
It's a matter of time to eventually find a point in which you can change your eccentricity back to the orbit you had before.
I am changing the eccentricity. The fact that I start from a circle and I go inside, that inside is an ellipse. That outside is an ellipse. So does that respond to your question? Yeah, I'm not going on circles. I'm going to slightly eccentric. I mean, you can make them crazy eccentric. Yeah. Because I wanted to make them look like they're close to each other, but I could go here on a very eccentric one, as long as I don't, hit the planet, and this would be maybe the fastest that I could get, where this periapsis is very close to the surface of the planet, and that is fast.
I thought you were just going to the little one before.
Yeah, no, it's not a circular one. Yeah. It's like this is basically a Hohmann transfer, except the two burns happen at the same location. That's the only difference. But there's still two impulses. When I was changing before same major axis and eccentricity, as I said at the beginning, I'm doing the same here. I'm changing same major axis and eccentricity at the same time. That's what happens when you are on any orbit and you just do one burn along the velocity. It doesn't matter if it's with velocity or opposite to the velocity. You're going to change same major axis and eccentricity. That's what happens. Because if you go back to the very beginning when we said, I give you R and V, and from these two you can compute the specific angular momentum and the eccentricity, and then from these you can continue and do all the other orbital parameters. You're changing these, you're going to affect those. And I am changing the, I know that I'm not changing the direction of velocity, that's a different story. I could change V as a vector without affecting E, that I can do. But we haven't talked about those. For example, a change of inclination, you can take a circle and say an equatorial orbit, and at some point, randomly, in any point, you just add a velocity normal to the plane such that your magnitude of the new velocity vector is the same. It's just pointing somewhere else, so now you have a new inclination. You haven't changed the eccentricity. We have to see that. But here I'm just pushing or breaking down. And so necessarily I'm going to change the angular momentum by doing that. Acceleration, I'm going to increase it, or braking against the velocity, I'm going to decrease h, and that in cascade, if you look at all the equations we've seen, will change your E and A. Not I, not little omega, not the ren, only those. Because we're doing all in plane. We're not changing outer plane characteristics other than the magnitude of h. Make sense? Whoa, okay, I'm not going to finish this. I have an example that gives you an idea of how you use this. We can set it up, at least. I am on, let me see what I have here. Okay, I have a slightly eccentric orbit. This is the periapsis and apoapsis, and their distances, I call this A, and I call this C, and these distances are 6,800 kilometers. This is actual radius, as far as I'm concerned. For once, I'm not giving you height, just to confuse you. 13,600 kilometers. And, okay. And I have a spacecraft right here. This is my situation. Maybe it's the space shuttle, but this has eccentricity, so I wouldn't say that's what it is. ISS doesn't have really an eccentricity. But I have a satellite in A, and I'm chasing B, which is on the same exact orbit. It's exactly in 90 degrees here, right? Through anomaly. Yeah, with the reface maneuver. And I want to do it going inside. So somehow I have to figure out how big of an orbit this needs to be. And not only I want to do it inside, I want to do it with one pass. So B goes from here to here, and that's where we meet. I'm not going to do it, I'm not going to allow it to go around multiple times. I want to do it one time. All right, so, names of the orbits as usual. So this inside is number 2, and this is number 1. There's nothing else to say, really. See, this is a Hohmann transfer, because I perform an impulse here. In this case, I slow down. I'm going inside. And then to go back to the original orbit, I'm going to apply the same exact delta V in the opposite direction. Make sense? I remove energy, and I put it back exactly the same amount. So what is the relationship here? If I call these, the time that is required to fly on this orbit from this point to this point, let's call it T, A to B. What is the main first relationship that you have to set up so that you can figure out the same major axis of this orbit, and once you have done that, you can figure out the burn that you need here? It's a timing issue, right? So what does T2 have to do to work? I don't know what that is. I have to figure it out. So the question is, what is that T2, basically? Because if I have T2, then I have also the same major axis. You use that relationship, you compute it. Nope. If they are the same exact period, I'm in trouble, I think. T2 has to be, this guy burns here, starts traveling on this trajectory, right? And does one revolution, one orbit. at the same, during this time, I want this other guy to just continue unperturbed on its orbit, and guess what? End up here when all this has happened. So T2 has to be T1 minus that time, right? Agree? And I have this, right? That's my start orbit. We'll figure out this. And this is the unknown. Once I have T2, I will know its semi-major axis, and I will be able to figure out the two burns to go to that semi-major axis and then get out of that semi-major axis. Actually, you compute the burn just once, then you double it up, and that's your total delta V, right? Okay, so T1 is simple. A1 is 1 over 2 that RC, these two radiuses here. Yeah, RC and RA. And I have it here, it's whatever it is, 10,200 kilometers. That corresponds, when you use that expression there, but solve for the orbital period, is 10,252 seconds. That's T1. Okay. That's easy. Now, TAB, how do you solve for TAB? No idea? We've seen it. Remember this two-way relationship we had between time and true anomaly? What was its name? You should have done an uncollected homework on this. The one that had to be solved numerically one way, not numerically the other way. Which of the two ways was not numerical? If I give you true anomaly, can you compute time without going through iterations? Yeah, right? The opposite was not that simple. So this time here, T from A to B, this is not a trajectory, by the way. This was just for me a way to, to cover that piece of this orbit, okay? This is just nothing. So the true anomaly here is 90, right? Because this is the closest point, this is the furthest point, this is the line of apse, this is the direction from which I count the true anomaly. So I give it to you. I know that theta in B is 90, or pi over 2. Agree? So if you invert Kepler's equation, this is what you get. The TAB is T1 over 2 pi. Remember that time times 2 pi over the orbital period was what we called mean anomaly. Is equal to the eccentric anomaly in B minus the eccentricity of orbit 1 sine of the eccentric anomaly in B. Again, we solved this in MATLAB. We see it in class. You should have done it by yourself. All right? So I have T1. This is 2 pi. What is this? And then I'll stop because I think time is up. How do you compute the eccentricity if I give you what I gave you on the board? Yeah, you use perigee and apogee. That's all you have, right? It's R C minus RA over RC plus RA. Sanity check. This is a closed orbit. It better have an eccentricity less than 1. So this makes sense. This is going to be less than 1. You can finish it yourself. I believe it's also on your book. They probably have even more questions than what I asked you. But what you do is, we'll finish it next time. You end up calculating this time, apply the relationship, find T2, find the same major axis of orbit 2, And from there, you can figure out the delta V's. Now, there's also one comment that we'll make next time, that you don't have to go just one time around. You can do n rotations on orbit 2, just making it very close to orbit 1. You wait longer, you reduce your delta V. But we'll finish it next time.